Okay, thank you for your notice. So let's get back to the presentation. As I was saying, the circuit description can be input in SPICE in two ways. Either using a graphical user interface in which you design the schematic, or by writing a text file in which the description of the circuit is given. Actually, the graphical user interface is used to get the schematic from the designer input, but SPICE translates each schematic into a .cir file. This is provided as input to the actual SPICE engine, which produces multiple outputs. Textual output, which can be displayed with the word processors, or graphical plots displaying, for example, input-output characteristics, frequency responses, noise plots, etc. Okay, so you can either use the textual description or the schematic one. In my opinion, you better use the textual description for the initial modules. Okay, so for example, the description of the schematics of of the op-amp, and then you can build out of the textual description a sub-circuit and use it to generate your own component to be used multiple times in the schematic editor. Okay, but we will see this both the options that you have. Okay, so this is basically what I've just said. So you can either direct simulate netlist files, so text files. In this case, the circuit is given in the form of a netlist. So each component, for each component, you specify the value of the terminals and the value of specific parameters. For example, channel length and channel width for a transistor, or resistivity, or capacitance, etc. Then you run the simulation, perform the analysis, and post-process the data. Or you can use a schematic editor simulation, which we will review later on. In each textual description, there are three main components. So in each SPICE netlist, there are three sections. First section is the model section, in which you specify the technological parameters. Okay, so for example, for transistors, threshold, channel length modulation coefficients, body effect coefficients, etc. Then you have a second part in which you specify all the elements of your circuit. So if you have an integrated circuit with let's say 10 MOSFET, then you list all of them, specifying how they are connected to each other and their parameters. And finally, the last section is the one in which you specify simulation comments. So again, operating point analysis, DC analysis, AC analysis, noise analysis, transient analysis, etc. Okay, so you have to pay a lot of attention at the beginning, because syntax may be a little bit misleading. Okay, so be careful try to split your circuit into sub-circuit or sub-components and simulate first independently each component. Okay. Well, first of all, let's discuss the model part. Okay. For example, the model for NMOS and PMOS devices. So you enter the model description in your netlist by using the .model command. Okay, so the .model command is used to specify all the parameters of a specific technology. For example, for an NMOS technology, you can specify the threshold. Okay, VTO. Yeah. Please keep attention. This is actually an O, okay, not a 0. Okay, so it's VTO. Kp is what we have called beta prime, so mobility time oxide capacitance. Gamma is the body effect coefficient or threshold voltage parameter. Phi is the surface potential. Lambda is, of course, the channel length modulation coefficient, and then you can find all the other parameters. These parameters here are related to the parasitics effect, okay? And you can find in your study material related to the MOSFET modeling all the details about these parameters. Okay, these are the same parameters that we have discussed when we have introduced the concept of parasitics capacitance. Okay, so here you can see the formula. So these are the formula implemented within SPICE. So channel width and channel length are not specified in the model, because these are design parameters. Okay, you control them. Okay, so the channel width and channel length are specified in the section related to the elements, because each transistor may have a different sizing, of course. LD is also a parameter related to a specific transistor, which is the lateral diffusion. And then lambda and of course VDS depends on the particular operating point. So this is a sort of recap of all the formula used within SPICE, okay, to run the calculation. Nothing really new, okay? Depending on whether you are in the linear region or in saturation, you multiply this term times this one or this one. This, again, are the junction capacitance expression. And in this junction capacitance, there are parameters related to the transistor sizing, such as the area of the drain, this AD parameter. PD also is a parameter which is related to a specific transistor, so it is a design parameter, is the perimeter of the drain diffusion. And similarly, for the junction capacitance related to the source bulk terminals, we have some device parameters, which are the area of the source and the perimeter of the source, and some technological parameter like CJ, MJ, CJ sidewall, MJ sidewall, and all the remaining parameters. Some other terms are related to the specific biasing condition, which are computed directly by SPICE. Okay. Again, these are transistor parameters, so these are not specified in the model section, rather in the elements section. And these are the technological parameters that you can find in the model section instead. So each technology has its own parameters, of course. So these are the specific parameters that you are going to use in your design project. Okay, so on top you can find the parameters related to the NMOS. Okay, with a threshold, beta, phi, gamma, lambda, etc. And then you will find you can look at the parameters related to the PMOS technology. Okay, this label MN is the label that we are going to use to specify that this is the model that we wanted to adopt. Okay, actually you can specify even more than one model for a single type of technology by giving different labeling. So in certain application you may have different kind of transistors, maybe short length and short with a short channel length or a longer channel length, which of course are related also to different channel length modulation effects. Okay. So the MOSFET is just the first example of the large number of components that you can place in your circuit. We are going to use resistors as well, capacitors, and independent voltage source or independent current sources. Okay. In some cases, you can use also voltage control voltage sources or this kind of, let's say, externally controlled sources. Okay, so E, G, H, and F. Depending on the specific application, they may be useful. We are not going to use bipolar transistor simulations because in this course we have just seen MOSFET devices. Okay. Each component is characterized by its own syntax in specifying the connections. Okay. So, for example, the MOSFET. In the MOSFET placing, we have to specify what is the node related to the drain, the gate, the source, and the buck. Okay. Then we have to specify channel length and channel width. We have to specify, of course, which model we are referring to, and we may also specify some other parameters like the area of the drain and source region and the perimeter of this region. There are multiple ways to enter the actual values. For example, you can use these abbreviations to specify the order of magnitude. Yeah, well, we are going to use a lot U, milli, of course, kilo for resistors in particular, etc. Okay, so actually you can either use this letter or the full name, or you can specify the magnitude with this scientific notation. Okay, they are basically equivalent. There is no need to specify the physical unit, so there is no need in specifying that capacitors are expressed in farad or channel length in micrometers, okay? Or, well, actually in meters. You have, of course, to specify the order of magnitude, okay? If you have questions, please feel free to interrupt me, okay? So, first thing to do, as I said, is then to specify the simulation command. Okay, the first simulation command that we will review is related to the operating point analysis. Okay, so this simulation command is simply given by this .op command without any additional specification. When you run this kind of analysis, you are assuming that all the time derivatives are null. Okay, it's a stationary analysis. So capacitors are turned into open circuit, inductors into short circuit, and the operating point results are given in a text form. Yeah, let's skip the mathematical details about the discrete solver implemented in SPICE. And let's jump to another important simulation command, which is the .tran, so the transient analysis. Okay, so this simulation indeed may be specified with additional parameters. For example, you can specify the duration of the time interval that you want to simulate. And also, you can specify the time discretization that you want in the output plot. Okay, so you can basically, within SPICE, you have a discrete solver. Okay, so it assumes that the time is discretized into fixed intervals, and in each interval it computes the actual solution. Okay, so you can specify basically the sampling frequency of this discrete procedure. Okay, let's try to run a first example of simulation related to this RC circuit. So this is basically, we can see it as a sort of low-pass filter. Okay, so when we apply the step input to this RC circuit, what we do see is that a certain change in the output voltage, which is somehow smoothened by the effect of the low-pass filter. Okay, so let's try to run this simulation. Well, you can download the script from Virtuale, or you can rewrite it. Actually, when you generate a script, you have to keep attention because you can do it with multiple editors, but you have to verify that the extension is .sir. Okay. Because multiple editor will save the script with a txt extension, and then SPICE cannot interpret that kind of input. Okay, so verify please verify the extension. So when another important comment when you use netlist is in the fact that SPICE never interprets the first line of your file. Okay, so in the first line of your file, always place a comment. Okay, so you can enter comment by using the asterisk. So everything after the asterisk is interpreted as comment, and then it is important that you have a comment in the first line. Okay. So in this particular case, there is no model section, because we have a very simple circuit with just conventional component like the voltage generator here, the resistor here, and the compensation capacitors here. I will get back to this comment here. Well, actually, let me jump at first in the study material. So first of all, I want to show you that, for example, when you place a resistor, what you do, can you read it? Hope so. You specify at first the name of its terminals. So basically, Rin is placed between this node, which is node in, then and the node out. Okay, so Rin is between in and out. Vin is placed between the node in, which is this one, and the node ground. Okay, and C1 is placed between node out and the ground node. Okay. In all your circuit, you should mandatory have the ground node placed somewhere. Okay, in the circuit. You can either enter this command GND or name it with a 0. Okay, so node 0 is the ground, and you should always have this node in your circuit. Then, after the specification of the connectivity between the different components, you have to specify the value, okay, of the circuit parameters. So, for example, this resistor should be a 2 kilo ohm resistor, so you enter 2K as a practical mean to specify this value. This capacitor, sorry, is equal to 100 femtofarads. Therefore, you enter 100 femto, okay, 100 F. Another important comment. You may have multiple resistors, okay, of course. So when you enter a resistor, you specify as a first letter R, mandatorily, and then after that, you can enter the name of the resistor. So in this case, this is R1. So I have specified R1. Similarly, for C1, C is the name of the component, the characteristic of the component. So this guy, C for capacitor. And then 1 is the specific capacitor we are placing in our circuit. And this is true also for MOSFETs. Okay, so the initial letter specifies the type of component, and then you enter the name of the device. The transient analysis here is specified with this command .tran, the one that I was introducing before. And then you have two parameters. The first parameter, 20 picosecond, is related to the discretization step. Okay. While 1 nanosecond is the length, the duration of the time interval that you want to simulate. Okay. You may introduce some additional parameter. You can use LT-SPICE manual to verify all the options that you have in the transient analysis simulation. For example, you may be interested in simulating a transient analysis from a given time instant, which is different from 0. Okay, so you can specify the initial time instant for your simulation interval. and so on. Finally, the script should be ended with the .end command. One last thing is related to this part here of the script. So we are entering a voltage source, so capital letter V. Here it is, an independent voltage source. And this voltage source is connected between input and ground. Okay, so in and GND. And then we have this command here, which is used to specify how this voltage independent source acts. Okay, so this particular command is used to implement piecewise linear functions, PWL. By using this formula, you specify a set of coordinates in the time and voltage domain. So basically here you are specifying that at 0 picoseconds, your piecewise linear function must be equal to 0. Then at 100 picosecond, your input function is still 0. Then you have at 150 picosecond, the input value, which is equal to 1 volt. Okay, so you see at 0 nanosecond, the input function is equal to 0. At 0.1 nanosecond, it is still equal to 0. At 150 picosecond or 0.15 nanosecond, the voltage input jumps to 1 volt. And the last specification is related to the value at 1 nanosecond, where the input is still equal to 1. Okay, so you have, in this way, you have specified just 4 points. In all the remaining time instant in between this point, you have a linear interpolation. Okay, so you pick up the closest point and you draw a line between these 2 points to specify the input value. Okay, piecewise linear. There are multiple alternatives. Is it everything clear?
Trying to simulate it.
Nobody.
No, I think it's just missing the line.
Okay. Okay. So indeed, we can try to run this simulation to see what happens. So to run the simulation, so basically you first open the script with the open command. You load the script, and then you run in this way the script. So when you push the run button, this window appears. Then in this window you will have to specify which traces you want to plot. You go in this menu, pick visible traces, and then you select the one that you want to display, for example, the input and the output voltages. Okay, this is it. Another interesting useful tool is the display of markers. So what you can do is to go on the text corresponding to the variable that you want to analyze. You left click on the name, and then this menu will pop up. And basically, by using this you can scroll this to verify point by point what are the actual values in terms of x and y coordinates. So in this case, time and amplitude. Okay. If you keep the left button pushed, you can move up and down the marker. Then if you want to add another marker, you can again select another variable and add the marker. Okay. You can also play with the with these quantities. For example, if you right-click on the variable, you may be interested in displaying the time derivative of the output voltage. You can do that by entering algebraic expression in this menu. So what I did is to right-click on this text, and then, for example, if you want to display the derivative, you use the command D, derivative of V out among brackets, and this is it. Okay, so you see that the derivative is this guy here. Okay, the time derivative in this case. Okay. Then, of course, you can cancel traces and so on. Okay, so it is quite intuitive, the menu, not too many comments, so you can just play with the tool. Okay. Again, are there any questions? Everything clear? Okay. So piecewise linear, the piecewise linear command is a very handy tool, but you may use also different alternative. You can use the pulse command if you this pulse command generates basically sort of rectangular input. Then you may enter sinusoidal function, exponential, piecewise linear, etc. Okay, so there are several different possibilities. You can find all of them in the tool manual. Okay. Then you can specify also as an alternative input which are stationary. So, for example, if you want to place a constant voltage generator, you specify the value DC. Okay, so you enter DC and then give the actual value. For example, if you want to place a 1 volt constant generator, it is let's say V1, node positive, node negative, and then DC 1. Okay. In some other cases, you may need AC generators. For example, when you are running AC simulation, then in this case, you can specify the amplitude, the phase value, quite unlikely. Okay, usually just the amplitude is specified. Okay. Similarly, you can place current sources in your circuit. The only difference is in the fact that the initial letter is capital I, or rather than D. Well, actually, SPICE is not case sensitive, so capital or small I is good. So this is the piecewise linear possible source. Again, this can be used for voltages or currents, and you see the idea. Okay, the one that we have discussed previously. So you enter time 1, and then the voltage in correspondence of this instant, time 2, V2, etc. Okay. this can be very useful when we want to test a step function with different slopes. Okay. In alternative, you can use this pulse command if you want to have also some repetition. Okay, so if you want multiple passes, then you can specify this pulse command. In this case, what you do is to specify the voltage in this plateau here, the one in this part, the top part, and then you specify the rise time and the fall time, which can be different, especially if you are trying to simulate a digital signal. And then there are some additional parameters like the time delay for the switching of the first pulse with respect to the null instant. And then you can also specify the pulse repetition rate. Okay. This interval here, pulse width. Yeah, you can control all the parameters of this wave. These are examples of exponential sources. Okay. Again, depending on this can be used to simulate the effect of a given controlling input. Okay. Truly step function are quite unrealistic in actual circuit, so it may be useful to simulate these trends. Sinusoidal sources actually are either pure sinusoidal or damped sinusoidal, so with a sort of attenuation in the time domain. Okay, so this was a detailed analysis of possible sources. After the break, we will review how to place MOSFET elements, okay, and the parameters that we have to specify.
Sei sicuro? Yeah. I just want love everything. And again, like I said, how is how is yeah, we don't have time to say. After the release, because they're talking about our and he said, yeah, these are the things we've done. Sì, allora I went to very hard, like this Friday, so I should have known. I was like, no, no, I'm not doing this. That's
grazie, non c'è dici. Cosa dici? Tu dici che ridi, ma non è tanto un cazzo. Ci devo aspettare così. Sì, infatti. Ma non può più.
Okay, so MOSFETs. The syntax to specify the MOSFET value is given in this slide. What is important when you enter a MOSFET in your circuit is the order of the terminals in the naming. Okay, so M is the capital letter which is needed at the beginning to specify that we are using a MOSFET. Name is the name you give to the transistor, could be M1, M2, etc. Then you have, this is an important point, drain, the name of the drain terminal, which could be also a number, for example, number 1. Okay, then the gate, the source, and finally the body. Okay, in principle, the MOSFET is a symmetric device. Okay, so you should be able to flip a drain and source arbitrarily. But this is not the case in LT-SPICE. Okay, it is important to understand whether one node is the drain or the source to properly use the equation embedded in the tool. Okay, so drain, gate, source, and body. Please remember this. Type is the model. So, for example, the model name that you want to use for this particular device. So, for example, MM. And then you specify the channel width, of course. So when you place a component in the netlist in the element section, you specify also all the design parameters. and the channel width and the channel length are indeed design parameters. Okay, so you have to specify this value. Please remember that the unit is not specific. There is no necessity to specify the unit in LT Spice, but by default, the unit is meters. Okay, so if you write L equal to 1, it means L equal to 1 meter. Okay, so in many occasions I've seen this slight mistake. Parasitic capacitances of 1 meter transistors are quite cumbersome to handle. Then you can specify the area of the source and the one of the drain. Basically, you can use the formula that are given here. Okay, so if you have a certain LDIF diffusion length, then the other dimension is given by the channel width, etc. Okay. Okay, same. So for the source and for the drain, you can do the same. Specify area and perimeter so that the estimation of the diffusion capacitances can be better performed according to, let's say, realistic parameters. Okay, so let's try to run a transient analysis like the one that we have seen before, but for this circuit here. Okay, so basically a CMOS inverter. So this simulation here is the netlist indeed is slightly more complicated with respect to the first one, because indeed we have the initial comment, okay, because the first line is not interpreted. Then you have the model section, okay, because when you enter a transistor, you needed to specify also the modeling. Okay, then after specifying the model by using the parameters that I gave you in the study material. By the way, actually, SPICE interprets each line as an independent command unless you don't use this plus sign. Okay, so when you add this plus, this means that the line should be just continuing. So these are the model parameters. Then you have the element section. Okay, so section. So first you plug one transistor using letter M. Then the name of the transistor is 1. Then you specify drain, gate, source, and body coefficient. Okay. Terminals. So in this case, we are using, this naming for the terminals. So this input node is called 1. The output node is called 2. And actually, this node here, corresponding to VDD, is node 3. Okay, so numbering the nodes rather than giving the names could be easier, okay, more quick, okay. But in some other cases, it can be useful also to use, let's say, letters, okay, or words. So, for example, transistor number 1 is this guy here. Transistor number 1 has the drain connected to node number 2. The gate connected to node number 1, and the source is grounded, so it is connected to node 0. Okay. In this sketch, you cannot see the bulk connections, but usually the bulk of NMOS devices is connected to the ground or to the lowest possible voltage, while the bulk of the PMOS is connected to VDD. Okay, so 0 and 0 are source and bulk connections respectively. Transistor number 2, by the way, then after specifying the node connections, you have to specify which kind of device is this one by using the name of the model, MN, and then you enter the dimension of the transistor. So the channel length is 2 micron, okay? You use the symbol U for microns, and the channel width is 4 microns. So shape factor is equal to 2. Then we enter transistor number 2. Transistor number 2 is connected to node number 2 with the drain. Then the gate is connected to node number 1, and the source and bulk are connected to VDD because it is a PMOS. And then you specify that indeed it is a PMOS by entering MP, the label of the PMOS technology, and then the dimension. Okay, so in this case you are specifying just the channel length and channel width without adding also information related to area and perimeter. These are secondary effects, but nevertheless you can also enter these ones if you want to run a more precise simulation. Okay, it is not displayed here, but you have also load capacitance, okay, connected to the output. So from node 2 to the ground, we have a 10 picofarad capacitance. Then you have a constant voltage generator. So let me jump here, maybe it is more visible. So we have this constant voltage generator. So capital letter V as initial letter, then VDD is the name of the voltage generator. This voltage generator is connected between node 3 and ground. And the value of the DC voltage is 3.3 volts. DC, because it must be constant. Okay. The input is given at node number 1, and it is a pulse input. Okay. So the pulse is oscillating between voltage 0 and 3.3, and these are all the time parameters that we have discussed in the previous study material. The transient analysis is performed between 0 times 0 and 1 micron second, and the discretization step in the plotting of the time instant is equal to 1 nanosecond. With this command probe, you can launch the graphical display. Well, actually, you can either use it or not. And the dot end simulation can be used to then verify what is and is the mandatory last command that we add to our simulation. Here you can find also .op analysis, which is commented. Maybe later on we can get back to this command. Okay, let's run the simulation again. When you push the run button, this new display will appear. Then we have to select the faces to be displayed. For example, we can see what happens to the input and output node it is quite pointless to display V3 because V3 is a constant voltage equal to VD. Okay, so you see the transient analysis. So V1 is a pulse. Indeed, the pulse is between 0 volt, the pulsing, and 3.3 volts. So this plateau here is 0 volt, this one 3.3. You can see that there is a very steep slope. Okay, so the rise time and the fall time is just 1 nanosecond, so very rapid. And then you have the other parameters. To be honest, I don't remember all of them, but if I remember well, the first one is related to the time shift with respect to the time zero. Then you have to specify t rise and t fall, and then the duration of the pulse, so the pulse, so-called pulse width, and finally the periodicity of the whole sequence. Okay, you can see that the transient occurring in the output voltage is not, let's say, symmetric, in the sense that we reach very rapidly the 3.3 volt limit, while the slope in the negative output is much slower. Okay, so and this is due to the fact that the sizing between the transistors is so that the PMOS is very large, while the NMOS is relatively low conducting. Okay. Again, questions? Okay, let's jump to the next slide then, which is related to the DC analysis. So the DC analysis, well, of course, it can be used to display the input-output characteristics. It is a stationary analysis in the sense that we suppose that in each point we have reached the stationary condition, so the derivative in the time domain are null, and therefore, again, capacitors are open circuit and inductors short circuit. So, okay, then you can report the DC result in a plot, and you can also sweep multiple sources, which can be interesting. So, for example, this DC analysis, it is used to display the current, the IDS current, with varying VGS voltages and varying VDS voltages. Okay. So, in this particular case, we are using the same model that we have used before. We have a quite simpler circuit in the sense that there is just the NMOS. The NMOS is placed with this command. Okay, actually, this sizing is not correct. Okay, you see in this case, channel width is 1 micro, channel length is 500 nano. And okay, so in this case, the naming of the terminals was done by using letters. So drain, gate, ground, and ground for this guy. Between terminal G and ground is the VGS controller. Between node D and ground, we have the VDS value. The starting point is this guy. So 0 volt and 0 volt, but actually this this value here is overwritten by changing the VDS voltage and the VGS voltage with the .dc command. Okay, so step by step, these initial values are cancelled and replaced by the discretization performed in the DC command. So the DC command, so let me close this one and this one. Do you want to? No? Yeah. No. You can open. Yeah. So model section, okay. Then elements section, and then command section. So the DC command requires some additional parameters. So first you specify that you want to sweep the VDS voltage. The VDS sweep must be performed between 0 and 2 volt, and 0.05 is the voltage discretization step. Okay, so the engine within SPICE is a discrete simulation. Of course, we cannot simulate continuous signals. Okay, so the discretization in the amplitude of VDS is provided by this step here. So 50 millivolts step in the analysis. VGS, the span of VGS is between 0 and 2 volts, but the step is quite larger, so 0.2 volts. Okay, so we are changing both VGS and VDS. Let's run the simulation. And then we have to display the curves. Okay. So the current I is displaced, and you can see the conventional trend, which is typical when you increase the VDS at a certain point, you reach the saturation region. Okay. So basically, this is quite normal. Okay. There is this parabolic trend here when VDS is equal to VGS minus VT, and this generates the saturation from the saturation point on. The curve is almost flat. Okay, the only effect is given by the channel length modulation, which is quite modest. Okay. DC simulation indeed. Okay, the simulation related to noise is relatively simple to be performed. You can just use the simulation command .noise. The only thing that you have to check is whether you are displaying the output noise or the input one. Please remember that the specification in your project is provided in terms of input noise. Okay, so just check whether you are displaying the output noise, or the input one. AC simulation are also very important. So AC simulations are used to verify the frequency response, stability of circuits in terms of Nyquist criteria. Therefore, we are going to use a lot this command. By the way, this command shall be used also for the second project that I'm going to assign to you, which is related to low-pass filter design. And obviously, when you want to check the response of a filter, you have to use the .ac command. Okay, we will get back to the simulation parameters for the .ac command. But let me skip to the schematic editor. So as anticipated, typing a netlist is just one possible way to simulate your circuit. An alternative is to use the schematic editor. I guess that most of you are familiar with this mechanism. So basically, you will find a library of component in your tool. So you pick up one of these component, and then you use the wiring tool to connect the terminals in the proper way. You have then to choose which kind of analysis are you in need of, and then you run the simulation, and the processing of the result is pretty much the same that we have seen in the text case. So the LT-SPICE user interface is quite intuitive. So basically, unless you have to replace a resistor or a capacitance, you are going to use this command here. So enter a component, and then some menu will appear, and among all the possible components, you will select the one related to either NMOS or PMOS transistors. Then you can you have multiple commands to copy and paste or duplicate elements, or also to change the appearance of the symbols, and of course zoom in and zoom out. Okay. An important specification is related to the entering of the MOSFET model, because in many typical applications, you will not interested in using the model which is already embedded by default in LT-SPICE, but you want to define your specific model of the technology that you are using. And to do so, you enter you open the schematic, a new schematic, and then go into the edit menu, then select the SPICE directive tab. This new window will appear, and then you can enter the model that you find in the study material. Yeah, for those of you who have the PC, you can try to do these steps. So open a new schematic in the file menu. You should be able to copy and paste the model from hopefully, or you should find it in the script that we have seen before. My PC is stalling. Okay, so now you find the text related to the model also in the chat. So if you want to cut and paste, so edit spice directive, and then when this window will appear, you can type the model or copy and paste it in order to specify the model characteristic. Then you press on OK, and this window will disappear, and you will have the model below. You repeat this for the PMOS model and for the NMOS model. Okay? Edit. spice directive, and then you enter the two commands. In 2 steps, you can remove or keep the plus, I guess. Zoom out, zoom in, etc. Okay? When you do so, you have all the equivalent of the model section in the schematic, okay? Then you need to place the transistors, okay? So what you do is to go to the add component command, push the button, and then pick up the PMOS or NMOS with 4 terminals, which typically has this symbol. Okay. Then click on OK and place the symbol in some place. Did you find it? Okay. Okay, then try to sketch this circuit here. When you enter the PMOS and NMOS transistor, you have to specify that you want to use as model the one that you have entered before. So right-click on PMOS, then type the model name. Okay, another important thing to remember is that even when you use symbols, one of these terminals is the drain and the other is the source. And you can spot the drain and source by considering that the source is the closest to the gate contact. You see that there is this contact here related to the gate. The source is the one closer to the gate. And you have also the body contact, which should be connected to the ground for NMOSes and to VDD for PMOSes. So you can try to use the schematic to perform the same simulation that you did before. inserite un altro PMOS e provate a simulare un source comune, ok? Con un PMOS come carico. Sorry, we switch to English. So please try to simulate a common source amplifier by placing a PMOS with a constant gate voltage as load, okay? You need to instance also a voltage generator to specify the value of VDD, of course, okay? So you need an extra component like this one. By the way, among the component menu, you will find also voltage, which is a constant voltage generator. Okay, you can right click and specify the DC value. So for example, if you want to plug the DC voltage, the VDD equal to 3.3 volt, you specify this value. Okay. Please remember that every circuit must have also the ground, which is placed by clicking on this symbol here. And then the wiring is quite simple. You place your cursor on one terminal, then on the second one, each time you left click and you create the connection. So this can be used to generate the VDD contact, and then you can pick up the PMOS with 4 terminals to see what happens. Again, an important comment is related to drain and gate and source connection. Okay, so the source for PMOS is the terminal at the highest potential. Okay, for PMOSs. Okay, so you have to flip this. Okay, you can use this command here. Sorry. For some reason I cannot. Okay, you can use this command to rotate this device and mirror. Okay, so that if you want gate and source placed on top, by using these two commands here, you can flip the symbol as you wish. Okay. Another issue is that you, in some cases, it may be useful to check your connection by controlling the netlist, the equivalent netlist which is generated. Okay, to do so, you can click on the View menu and then click on the SPICE netlist menu. Okay, now this TXT will appear. And this is basically the translation of the schematic into a network. Okay, so in this schematic, of course, it is pointless to have this device connected in this way, but automatically LT-Spice can generate the .CR script. And as you see, V1 is connected between node null 1 and node null, which is the ground, and the value is 3.3. M1 has the drain connected to node 1, okay, which is not good because the drain should be the other one. The other one. So M2 is indeed correctly connected with the source, which is connected to VDD. Okay. So again, please take into account that the symbol. It is important to specify the right connection for the drain and for the source. Okay, so this so this guy can be cancelled. Okay, we want just this one. Okay, then you can do the same for the NMOS. Okay, the NMOS has the right model here. The PMOS model must be added. Okay, and then right-click and specify the MOSFET model with this comment. Okay, second mandatory break. Okay, then after the break, we will start reviewing the project design strategy. Pronto? Sì, Carmela, mi sto spostando, sono in un palazzo vicino alla collina che evidentemente è poco raggiunto dal segnale. Eh, eh. Ho capito. Mm. Sì, sì, sì. Te, te- ti ho messo tutto nella mail. C'è la descrizione, il motto, ne ho messo uno al volo provvisorio e poi i dati sui finanziamenti. È tutto nella mail. Sì. Non so se siano 300, non so se siano 300 caratteri, però poi senti, esatto. Mm. Sì. Io provo a sentire. Ok, io in realtà non ce li ho, però provo a sentire Alessia Cariani che era in Pricefish e forse aveva tutti e due i partner dentro. Sì, non mi senti più? Pronto? Pronto? Pronto, Carmela? Sì, io finisco lezione alle 6, quindi sì, va bene, perfetto. Ok, a dopo, ciao.
Non potrebbe, ma non sa di non potere, allora lo fa.
L'estima se fa male spesso, quello è...
Neanche così tanto spesso.
Se io non c'ho quello. Vai!
Okay, guys. In this last hour of this slot, would analyze how to use LT-Spice for the specific project assigned to you. So I'm quickly skipping part of the study material to jump to this section. So here you can find some possible resources. Actually, these are quite outdated, so maybe you can simply Google LT-Spice and find more recent documentation. I've seen that most of you have already downloaded the program, so let's jump to indeed the op-amp simulation task. Okay, so first of all, in the last class, I gave you sort of a strategy to define the sizing of all the elements of the project. I mean, even if it seems all straightforward, you may experience some difficulties when translating this strategy into a practical circuit implementation. Because in these, there are some approximation that we made to find the transistor values, sizing, etc., which are not made by LT-SPICE. So, for example, we didn't consider the effect, the body effect, okay? While in some cases it may play quite an important role. So you have to use the strategy as a compass to understand the basic mechanism of the circuit. But if you find some discrepancy, don't be, let's say, too much surprised. Okay, so you may see some slight variation in currents and voltages in your circuit. In some cases, these variations may force the device to work out of the saturation region, and this is critical. Okay, so first thing that we have to check is to verify that all the devices are in saturation. And if not, try to modify the circuit biasing and sizing to get this result. Okay, so this is the most important thing. In some cases, the discrepancy will be very high. Okay, in that case, there may be a mistake in the netlist itself. Okay, so wrong contacting, wrong let's say connections, flipping of PMOS with NMOS, or grounding in wrong positions. Okay, so you can double check this by using the netlist. Okay, so as you can either use the schematic to sketch your circuit, or using the netlist, or you can view the netlist from the schematic, as I've shown you before. So double check all the connections in case of completely unexpected results. The two-stage op-amp, well, actually the device that you have to simulate is this guy here, okay? But my suggestion is to start from a simplified version in which the biasing circuit is substituted by a very simple biasing like this one, in which you place a current generator with a very accurate value. Okay, so by using a current generator rather than an actual circuit with the transistors, you will find much easier to have the desired voltage here at the gate of transistor N8. You can even replace M9, that is the transistor in the linear region, which is used to achieve the resistive effect and the nulling zero with an actual resistor. Okay, R1, let's say, or RC, rather than a PMOS transistor. Then you can start by checking the operating point for transistors M6, M7, M5, M1, M2, M3, and M4, and then run the .AC, .DC, .tran, and .noise simulation. once you verify the meeting of the specification with this command, we will get back to this problem later. Then you can add the full circuit. Okay, so the full components with a complex biasing network with M9 as a nulling resistor. If we look at a project specification that you find on Virtuale, you will see that the model is the same for all of you. The main specifications are also the same for all of you. The unique difference is in the noise specification. Okay, so depending on your matricola, the last digit of your matricola, you will have a specification related to noise, which is either 22, 24, 26, up to 40. Okay, so the luckiest guy is the one which has 9 as the last number of last digit of the matricola. Okay. However, even if this guy seems to have the easiest specification, there is a noise and power trade-off. Okay, so this means that the guy with the more relaxed specification on the input noise must have a circuit which consume also the less. Okay, so there is a noise and power trade-off. So those who are requested to have a very low noise input values are somehow allowed to achieve an higher power consumption, and vice versa. Okay, so when I will judge your project, I will place your results along this hyperbola. Okay, so once again, if you have a specification relaxed concerning noise, then you should try to get a low power dissipation in your circuit. Okay, so there is no luckiest. Okay.
I heard one.
Okay, so then indeed you jump to the full circuit with all the connections. So my suggestion for the design strategies is indeed to create at first a simpler version of the op-amp and save it in terms of netlist. Okay, so dot circuit. Okay. With the biasing network realized with an ideal current generator and an actual resistor in the compensation network. Then connect the negative input terminal to Vout. Okay, so this is like connecting the op-amp in a unitary buffer configuration. So output connected to the negative input. Then place the positive input, control the positive input with a constant generator, and the value of this constant generator should be compatible with the voltage input common mode range. Okay, so you have a specification related to the common mode range, so pick up a value within this range and use this value to drive the positive input of the op-amp. Okay, so this guy here. Okay, so you connect this node to the output, and this node to a voltage generator whose value should be within this range. So between 2.1 and minus 1.3. Okay, so let's say 0 volt, for example. Okay. Then you run a .op simulation. .op operating point. With the operating point, you get a log file in which all the VDSs, VGS, currents are reported. Okay, so you can check whether your device is indeed in saturation or not. Okay. Once you have performed this check, by the way, this is valid for this circuit in which all the transistors work in saturation. In this circuit here, M9 will not be in saturation because it is in the linear region. Then you can run the other simulations, and finally you jump to the new circuit with all the complex bias network and RC substituted with M9. And you run again all the simulations. Again, starting again from the .op simulation, operating point. So this is an example related to a folded cascode design. Okay, so first of all, sketch the schematic on paper and give a name to all the nodes of your circuit. So you can see, you can use numbers. Okay, so for example, in this case, this node here is grounded. Then this node is node number 2, 6, etc. Okay, so you annotate all the numbers related to one particular node. Of course, this node 6 is the same node that connects the drain of M1, but also the drain of M4 and the source of M6. Okay, this is just one node. Okay, same for node 5. Node 5 is the drain of M2, but also the drain of M7. The source of M7 and the drain of M5. Okay, this is just one node. Okay, so you sketch on paper all these numbers, and then you design the netlist. Okay. One interesting option is then to build a sub-circuit out of the netlist. Okay, to create a sub-circuit, you use this command, the sub-circuit, obviously. This command specifies the name of the device, the inputs, and some parameters. Okay. Then you have the netlist, which may be related to the input parameters. And then once you have designed this sub-circuit, you can reuse it multiple times. I will see how. I will show you how. So for example, sub-circuit related to the folded cascode example that we have seen before. First, you enter the model parameters. Okay. Then you use the command sub-circuit. You name the component, for example, folded cascode op-amp. Then you specify the input and output port. So the input will be at node 3, 1, and 10. Okay. Then you instance all the devices. Okay, all the transistors belonging to the circuit. For example, these two guys are the elements of the differential pair. So M1 has the drain connected to node 6, the gate connected to node 3, the source connected to node 2, and the bulk is grounded. Okay, so if we go back to this circuit, we have the drain connected to node 6, the gate connected to node 3, the source connected to node 2, this node here, and finally, for all NMOSs, the bulk should be either grounded if ground is the smallest voltage, or to VSS if you have this voltage here. Okay, because we We need to have a source bulk junction in off or in reverse condition. Okay, this was an example for M1. After the specification about the terminals of this component, you have to specify the model that you want to use, so model MN in this case. So this is the technological part. Then you specify the dimension, channel length and channel width, okay? And you repeat this procedure for all the devices. Of course, channel length and channel width will be found with the procedure that we have sketched in the previous class. So first, you run all the calculations on paper, or on MATLAB, or on whatever simulation program you want to use. Then you translate the value that you found in terms of shape factors into these design parameters. Okay. You repeat the same analysis, the same procedure for all the components. You need to add also voltage generators and current generators when necessary. For example, in this case here you have a current generator, then VB1 and VB2 are voltage generators. So you add also this component when necessary, and of course you had the VDD. Okay, you need the power supply, VDD and VSS in your project. Finally, you end the sub-circuit with this .ends instruction. Okay, .ends and name of the sub-circuit. Okay, then you save this file. Please keep attention to the extension. Okay, so you will try, in some cases, you will try to save it as .sub, but for some reason, the editor within LT-SPICE will add an extra .circuit extension. Okay, check this. In case you find this error, remove the last extension. Okay. You can use a file explorer to do this. Okay, because otherwise you cannot reuse this sub-circuit as a library component. Okay, so that sub and that's it. Okay. Okay. Once you did all these steps, you right-click on this line. Okay, right-click on the blue line. This menu will pop up, okay? Then you push the Create Symbol button. By the way, you should have this, the whole script on Virtuale, if I remember well. Let me see. Yeah, you have this folded sub. So if you want to test this procedure, you can load it and try it. So. Another important thing, in some releases of LT-SPICE, there are some troubles with the administrator rights. Okay, so when you generate a symbol, my suggestion is to run LT-SPICE with administrator rights. So again, right-click on the program, select execute with administrator right, and then use the program. Okay. Okay. Then select create symbol, and then a new window will appear. Okay. First thing that you have to do is to go in the edit menu. Click on the attribute tab, and then push edit attributes. Okay, this new menu will appear. The important thing is that as symbol type, you have to select the symbol cell. Okay, you have two options, if I remember well, cell and block. Okay, pick up cell. Okay, actually, when you first generate the symbol, the appearance of the symbol itself will be just a simple rectangular block. Okay, so you can edit this with a menu that you have on top of the window. So if you want to generate a conventional triangle which is used for op-amps, you can draw the triangle by playing with the symbol. Okay, you can also move the input and output port, give the right name. You can play with the draw menu. Okay. Okay. Okay, save, and basically this is it. Okay, so when you complete this procedure, you have a new symbol among the libraries which is included in LTSpice. So you go into you go in, you select the component, okay, and you will find also your symbol among the many that you have. Actually, well, fortunately I've shut down the LTSpice here, but you should find an auto-generated library. You right-click on auto-generated, and you will find your symbol. Or if you cannot find your symbol, you can try to add the library directly as a Spice directive. So you enter the path in which you have saved your component. Okay. And then you can try to run a DC simulation like this one. Okay, so you connect the op-amp with this non-inverting configuration, and then you simulate as if it is a normal op-amp. Okay. Another important issue is related to the fact that these op-amps, the one that we have seen in our classes, the folded cascode, the two-stage op-amp, are meant to drive capacitive loads. Okay, so high impedance loads. If you want to test your op-amp in an inverting configuration or in a non-inverting one, make sure to use very high valued resistors, so 10 gigaohms, okay? So that the value of this resistor does not affect the transconductive behavior of the op-amp, okay? So when you run this test, use very high valued resistors. Okay, then how can we check that we have met the specification related to the input common mode voltage range? Well, what you can do is to connect your device with as a unitary gain buffer. So again, connect the output to the negative input. Okay. Then run a DC simulation. This load resistor is not present in our specific application. Okay, so we have just a load capacitance. But run a DC simulation to display the variation of V out with respect to V in. Okay? You will get a DC curve like this one. So with the sort of saturation when V in increases, and also this sort of negative step when Vin decreases. While you will have a central part of the characteristic in which the slope will be rigorously 1. Okay? The input common mode range will be coincident with the portion of the DC curve in which the slope is equal to 1. Okay? Because when the devices are forced out of the saturation region, all the nice large gain will disappear, and therefore we will not able anymore to use the VO pump as an ideal open. Okay, so when you run this simulation, check where the slope is actually equal to 1. You can use the derivative command to compute the slope. So you can even display the derivative. Okay, so if rather than V out you display the derivative of V out, you get exactly this result. This was a bad move. All stealth again. I think that the only way now is to proceed basically, what I was trying to do is to sketch what should be done here. So rather than displaying V out, you can display the derivative of V out to see when this derivative is equal to 1. Okay, the derivative of V out with respect to V in, which is basically the slope or the gain of the circuit. Another issue is the simulation of the output swing. Okay, to simulate the output swing, my suggestion is to connect the O pump with this configuration here. So an inverting configuration. This means that here we have, sorry if you cannot see it, but here you have the positive input, here you have the negative input, and then you use this resistor, so that as you may remember, when you have this inverting configuration, the out should be minus R2 divided by R1. So in this case, this quantity is equal to minus 10. So indeed, you have an input-output relationship which is characterized by a trend like this. The output swing is the one in which indeed this slope is rigorously equal to 10. Okay, so again, you can compute the derivative of V out, D and V out among bracket, and display this quantity. When you see that this derivative is equal to minus 10, this corresponds to the limit of the voltage swing of the output. Okay, at a certain point we have saturation because the devices are out of the saturation region, and the bottom saturation, which is induced again by transistor exiting the saturation region. Okay, so you use this configuration by picking up the symbol, generating the schematic, using very high valued resistor, 10 gigaohm and let's say 1 gigaohm, and you run the .dc simulation. Okay. The simulation of the slew rate can be performed by connecting once again the output to the negative input, so unitary gain buffer configuration. You apply a step function at the input, with a very steep slope, let's say with a rise time of let's say 5 nanoseconds or even less than that, and also a fall time equal to the same interval, 5 nanoseconds or 1 nanosecond. And you see what happens to the output. Okay, the output should follow the input with a certain delay, and with a given slope, which is characteristic of the slew rate. So this trend here will be steeper when the slew rate performance of our device will be better. Okay, so the maximum derivative of the output in the time domain is given by the slew rate. That's what we have called the slew rate. So if we have a very steep input transition, then the output should follow also following the slew rate performances. Another important issue is related to this value here and this one on top, given to the input. Okay, the minimum and maximum value should be all compatible with the input range. Okay, the common mode range, because if you provide an input when you are out of the common mode input range, then you cannot get a decent output, because again the devices are out of the saturation region. Okay, so this quantity here and this quantity here, so the bottom and top value of the input should be compatible with the input common mode range. This value here and this one here. Okay, a transient analysis, of course, is necessary to measure this phenomenon. Okay, this is the last slide of this group of slides. What is missing here is the AC simulation. this was somehow discussed before. So the AC simulation, the AC analysis can be performed in open circuit condition. So you set the negative input to a constant value. Let's say compatible with the input common mode range. So let's say 0 volt. And V plus will be set at DC equal to 0, like V minus, and AC equal to 1. Okay, so the command will be dot AC, and then you have to look at the syntax of the dot AC command. The dot AC command is characterized by the starting frequency, the stop frequency, and by the way, the number of points within each decade or octave, or the number of points in general. So please look at the syntax of the dot AC command and use this command to run the simulation. Actually, you can either enter the simulation command as a SPICE directive, or use the simulation menu that you have among the top menu, okay, in LT SPICE. Okay, guys, my suggestion is for you is try to start the project as soon as possible, okay, so that you will benefit from the fact that we have just analyzed this project in the classes. Okay, so and if something is not clear, get back to me so that I can try to clarify better this activity. Okay. Starting from tomorrow, we will start the second module of this course related to analog systems. Okay. Thank you very much for your attention, and see you tomorrow.
The deadline of the project, when was it? Because I don't remember.
There's no deadline. Okay. Please deliver both projects I'm assigning to you about, let's say, 2 or 3 days before giving the oral exam. Okay. So depending on when you want to take the exam, then you will send me the project.